Bringing up this analogy, so you had sets, functions, sets of functions, vector spaces, linear transformations, home. The linear transformations between two vector spaces, right? There's also another one. Composite of functions is a function, right? Over here, it is a trivial check. If these are linear transformations, then so also is this. Okay, it's just trivial. Okay, check. The things to check for you to check. Okay, so you see, there's a kind of a parallel coming up. Okay, so what is the parallel? Sets, functions, sets of functions, composites of functions, composites of linear transformations. Composites of functions and the identity. So in this line, what I am going to draw is an exact analog. So what is, let me have a nice color. So over here, vector spaces. The symbols don't matter. That's why I kept it same. Linear transformations. Exactly the parallel of functions. Okay? Home sets. Okay? Composites of linear transformations. Then the identity, linear transformation. Okay? And we will, another thing we also saw. We also saw the zero vector space. And we saw the empty set. The empty set, remember the zero vector space, it had only one vector, the zero vector, right? 0 plus 0 is 0, lambda times 0 is 0, so it's obvious how to define it. So that's the analog Remember, the empty set, that was the smallest subset. I'm not coming to a sub thing now, but it seems. So, we will go on and see how much of this analog can we go on drawing. Okay? As we go on. Next time we will see subspaces. They will be the analogues of subsets. Okay? And in that case we will see exactly that the zero vector space plays the role of the smallest vector space. Okay? Let's place the role of the smallest vector space. Okay? So we will see subspaces. We saw intersection of subspaces. Sorry, intersection of subsets. We will see what the intersection of subspaces. We saw union of subsets. We will see it over here. What is it? Okay? And so on. We will see. We have this analog every time in our mind. Okay? So if you understand one of them, you shouldn't have problems in understanding the other. Let's stop it. Which one? Okay. Yes. But we have our tutorial session, right? So we join after 10 minutes. Okay? After 10 minutes we join? All right. Thank you.
Do you even have anything to ask James?
John. With videos on YouTube. Which one?
Well, I know there's actually now done by Yeah, no, I've seen it, yeah. But this one from previous years, right?
Yeah, this is from
I know.
Yeah.
I've got that.
When it transformed to the last time, the law has
Changed, so
yeah, when it transformed to the last chapter, you should feel satisfaction.
yeah, because what I presented for today, right?
Yeah, this is what he said last week. I think that's what when it transformed.
That's what you said.
Because I was that he picked people, but I just want to see about the
Yeah, I'll ask him more general question in terms of that. But no problem. Really comfortable.
What course are you doing? Are you doing math?
English, that, doing applied, that.
Well, too, I mean, what?
I really want to do Yeah, and it is what it is.
Yeah, I took 4.
Last year.
I'm also
I get what's happening with this.
And the multiplication is get a multiplication in the way the learning was
We've got a practice.
yeah, the
issue is always how this one.
yeah, that's also what I'm going to say.
Yeah.
I'm doing other subjects.
I did recruitment, but you count at the beginning, but
Yeah.
I have got to like another case.
Yeah, that's how they come.
Slightly useful.
Yeah.
It's as if she's doing.
Yeah. I heard the engineering and actually funny to see the ease of it.
Just take a line.
Yeah.
Okay. How is it related?
You just try to keep up with web now.
Then you have to deliberate. Professional database, but the title as well.
The point of this is to go into machine learning and machine vision.
Okay, no, you can very specific.
Yes.
That one, right? I thought I did, but
Okay.
gradually using machine learning.
Okay, so let's resume. Yeah, we resume again. Okay, thank you.
Machine learning.
Okay, so the video lectures for first two are already on the website, on the additional resources. Yeah. And I have also put up the lecture schedule for March. Okay. March is going to be heavy. There shall be 8 lectures, 2 each week. Yes. Well, let me finish this. Unfortunately, I could not get hold of weekends, so I had to put Tuesdays and Thursdays. It is from 3 to 6.
2 p.m. to 6 p.m.
3.
3 to 6.
3 to 6. Yeah, getting hold of weekends during March, because you see, the other departments also are now getting geared up with their practical sessions and so on. So the whole of weekends are completely booked. So it becomes very, very difficult. So that's the best that I could produce, I could get. Okay. But the lectures will still be available.
On the
Yeah. So, and you can always make up meetings with me using my UNISA, and also Skype sessions are possible. Okay, so there are alternatives. All right. So now, coming back to questions. So this is the hour for your doubts, queries, up to what has been done up to this point of time. So there was some query from someone with linear transformations. Is her question answered?
Sir, no, not really.
Yes?
My question was, if you have a matrix A and you have three vectors within the matrix, A1, A2, and A3, and A3 is a zero vector, and how do we define X3? Is X3 going to be 0 or is it going to be free?
1 minute. So here is our next example of so suppose we have suppose if we have any Rn, remember when I write this X, I mean that this is an n tuple of vectors, n tuple of real numbers, which looks like this. And when I shall consider it as a matrix, I shall always consider it as a column vector like this. Okay? Now you give me this matrix whose A is an m cross n matrix. Then this map this is a linear transformation. So each m cross n matrix gives me a linear transformation. In fact, we will show as we go on that every linear transformation from an Rn to Rm is actually given by a unique matrix, and that linear transformation comes in this way. So these are precisely the linear transformations, but that is much later. We'll come back to it. So now your question is, suppose if you have A, so I'm writing the columns. So this has n columns. So these are my columns. So each one of C1, C2, Cn come from Rn. Okay, because it has m rows, so each one of them come from Rn. Okay? Now what is Ax? What is Ax? Well, you cannot write it in this, you cannot quite write it in this form. You cannot quite write it in this form, but to come to your question in specific, you are saying C1, C2, C3. Okay?
Yes, sir.
And your last one is the zero vector.
So can I please make C2 the zero vector, because this is in reduced echelon form, so it's in the augmented form.
So your C2 is the zero vector.
Yes, sir.
So you have a matrix which looks like this. Okay?
Yes, sir.
And then what is the linear transformation doing? So what is AX? So AX is and that is now what is your question?
My question is, when you write the solution set in in parametric form, how do you define x2? Is x2 equal to 0 or is x2 free?
See, you are going much faster than I have done up to this place. When you say that this AX is equal to some B, what you are telling me is A1 x1 plus C1 x3 is B1, A2 x1 plus C2 x3 is B2, and A3 x1 plus C3 x3 is B3. No more. So you are now saying something further, that it is in the echelon form or something like that, which we have not discussed. So the matrix looks like this. So possibly something here. Right? So then, if you say that this is equal to then you are actually telling me x1 plus c1 x3 is b1, c2 x3 is b2, and this side, unless your b3 is 0, it has no solutions. So b3 must be 0 to have a solution. This is C2 x3, and then what is the solution? Well, you can immediately see from here, if C2 is non-zero, then x3 is, you can evaluate, and hence you can evaluate x1. And x2, well, okay, let's do it. This is minus B2 upon C2, and x1 is B1 minus C1 by C2 times B2. Okay? So your solutions come up like this. They look like this one, and right? So if you know your x3, then you know your x1. So it is actually dependent upon x2 and x3. So these are the variables in this parametric form that all the solutions are represented like, And okay, we'll come back to this, I think, in the next or the lecture after that.
Okay, sir. Thank you.
Yeah, she's done, I believe.
Okay. When you're finding the solution x3, why did you get a minus sign?
Did I? No, sorry. Yes, it should be this.
Thank you.
Yeah. Okay. So, yeah, any further questions? Any more questions? But we'll come back to this. We'll come back to the solutions and so on. Yeah.
Sir?
Next. Yes?
Could we please go back to preservation of the scalar multiplication?
Yes.
The part where it's x, y, arrow, x, f, y, could you please just quickly explain that to me again?
I just needed this top horizontal map, and that is what I was defining. So R cross V to R cross W. In fact, let's settle this once and for all. Once and for all, let's settle this. So, what I'm saying is, suppose we have one minute, let me finish this. Suppose we have two functions. Okay? Then from the Cartesian product of x and so Cartesian product of the domains to the Cartesian product of the codomains, we have this map which we write as f cross g, and what does it do? It takes a pair and takes me to fx and gp. So it takes the pair, evaluates by f and g respectively, and gives me the answer. Okay? So, over here I have taken the identity map over the reals. That's my first, that's playing the role of this first function. And the given linear transformation from V to W is the other one. So that gives me this function 1R cross F. So that's this function. We have used this function even earlier, remember here. So on both the coordinates, we took that function F. Okay? So what I was trying to say is, that given this f, I immediately have, well, this is just from set theory, I immediately have this function, and the preservation of scalar multiplication is nothing else but the commutativity of this diagram. We shall say such diagram commutes. What do I mean by this? See, this diagram has 4 nodes and some arrows. So whenever you take a path by an arrow, so 2 nodes, say R cross V and W, there are 2 paths. One, the top horizontal and vertical, or the left vertical and the bottom horizontal. When I say that this diagram commutes, I mean to say that if you take any 2 paths between these, any 2 nodes, okay, those 2 paths are equal. That's what I mean. So I mean that this function, which is the composite of the top and this function, which I now draw in yellow, which is the composite of the bottoms. Okay? These 2 are equal. That is the meaning of this. That is the demand of this preservation. That is the meaning of this commutativity. Okay? Similarly, over here, in the previous one, there are 2 paths from this top left corner to the bottom left corner. Okay? One is this, and the other is this. What I am saying, the demand for preservation of addition is saying that these 2 functions are same. Okay? So that's the whole idea. Is it clear now?
My question was, you know that those things in brackets, x comma y, I don't know what this arrow is called, but it's like line and there's like an arrow, x, f at
Yes,
y.
we call it maps 2. We call it maps 2.
Max 2.
No, maps 2.
Oh, max 2. Okay, so
Maps 2.
Oh, map 2. Okay, I have it now. I was asking, so x, y, does it map to x, f at y, meaning that x stays the same and y
Yes.
is the one that transforms to f at y?
Yes, because I have taken the identity function on the first coordinate. That's why x stays to be the same.
Oh, okay, so is x our real number?
Yes, yes.
Is x our real number? Okay, sir. Thank you.
Yes. Yeah. Next. Next. If you have any questions, even from the self-assessments, up to this time, whatever we have done. Okay.
Sir?
Yes?
So could you please just state all the things that we need to, all the things that we need to state again to check a linear transformation? You said that we need to check if f at 0 is equals to 0. We need to check that u and v are vector spaces themselves and...
One minute. So here is the flow chart for the same. So here is the flow chart. So you are given this function. So your first question that you address is V and W are vector spaces. If the answer is no, you stop. Your answer is, it is not a linear transformation. If the answer is yes, then your next check should be whether F0 is 0. Answer is no, you stop. Answer is yes, whether f of minus v is minus of fv. Answer is no, you stop. The answer is yes, you check this, answer is no, you stop.
Written with minus.
In fact, I should say a little better.
Minus, isn't it?
Yes, probably positive.
That's right. F of 0 is a yes, and then it's f of minus v.
Oh, is it
Minus. There are two negatives there. No, I'm not sure. Negative.
So there's a double negative by f negative v is equals to negative f negative v.
Sorry.
How do I erase this?
Okay? Now in most of the problems, in most of the problems, these steps these two steps are very, very clear intuitively. For instance, look into example 2. If we look into example 2, we see it's very clear. Immediately we can see f of minus 1 is not equal to minus over f1. Okay? So we stop immediately. But in most of the cases, we might have to go up to this level and decide. Okay? But in many cases, we could even stop very trivially in the first or second phase of check. So it just saves your computation time if by looking into the example you can spot such no, either to this no or to this no. If you can immediately spot it, don't go any further. So you should immediately see the first time when you can throw it out. That will save your computations to a great extent. But in general, this is the flow chart for checking whether f is a linear transformation or not. So this should be the general algorithm, but yes.
Is this where all the marks come from? Like in the exam when you're writing?
Question of marks is a little bit different, but obviously mark allocation comes from here, because if I think that just by looking into the example you should be able to decide either here or here, then there would be lesser number of marks. But if I know that doing such a check would be difficult, then there will be more marks, and if I know that you have to go up to this third tick, then I'll do that. But often I believe it is not right to look into marks, because having said so, sometimes I often if I might, because marking is actually a matter of relative, right? You can give the same question 5 marks, where there are 5 points, 1 mark for each point, and you can give the same question 100 marks, give 20 marks for each point. So how will it matter? So just don't look into marks and try to decide. It's better to understand the problem and go on for the solution.
Okay. On the page that we were working on, is B to E are U and V vectors?
Which one?
Sorry. The thing starts with saying a linear transformation from a vector space V to a vector space W is a function phi f dot dot V. It's just before the example. Yes. Are V and W in B to E vectors?
Yes, V and W are where is W? V and W are vectors. U and V are vector spaces. Sorry, V and W are vector spaces. U and V are coming from V. So they are vectors, obviously, yes.
Oh, they are vectors in V.
Yes.
Oh, okay.
Yeah.
So this is my second last question.
Yes.
Under number 7,
yes.
There's the next page.
Yep.
There is high 1. It's the first line, then the second line, then the third line. I'd like to ask what happened to the y plus lambda y prime?
Remember your function pi1. Pi1 was the function from V cross W to V, whose input is an ordered pair, and it suddenly forgets the second coordinate and returns you the first coordinate only.
Okay. Thank you, sir. And my last question has to do with number 8.
Okay.
You know, with the notation, Fg goes to F plus G, and F plus G goes to V to W.
Remember, this one, here, we are defining a binary operation on the set on this set. So we are defining a binary operation on this set. So it should be a map from the Cartesian product of that set with itself into itself. So hom VW cross hom VW, that's the Cartesian product, and the codomain should be hom VW. So what are the members of this domain? They are pairs, and each one of the elements of that pair, this F and this G, are actually members of hom BW. Okay? So what do I have to do? I am defining a binary operation which takes the pair Fg to F plus G. Now, F plus G is a linear transformation from V to W. So how should I define that function F plus G? So that's the definition of this function. So this is the definition of the function. Okay? So I have to get it as a function first from V to W. And that is the definition of this function. And then I showed here, where is it? Yeah, this is the place where I showed that that function which I defined by F plus G is actually a linear transformation. So this belongs to. So by the end of this, I have said that therefore F plus G is actually a member of hom V plus W. If F, G are already members of hom VW. And where did I require this? I required that here. Okay? So, in the end, I have therefore defined the binary operation over here. Okay? So it has many layers in this definition. The first layer is I'm going to define a binary operation on hom VW. To do that, I must first define a function. This one must be defined as a function, which I did here. And then I must show that this function is actually a linear transformation to make it a valid member of hom VW. So, there are at least 3 layers over here. Okay? Same for the scalar multiplication case. I have to show that there is a scalar multiplication on hom VW. That means I have to give a map from R cross this to home VW. So I'm doing it. I'm saying that I shall denote this by lambda f, but this has to be a function at least. So that is the definition of this function. I'm defining lambda f as a function now, and later on I have shown over here. So this, therefore, I have shown that lambda f is a valid member of home VW if f is. Right? That is what I have shown. And this is where did I require that f is? I required it here. Okay? So you see there are 3 layers in this definition. Okay? So first layer is I have to define the addition or the, so when I'm defining the binary operation, it is defined on a set. This is a set of functions. So I define what do I mean by addition. First it must be a valid function, and then it must be a linear transformation to be a member of that set. Okay? So that's what, those are the layers. I hope it should be clear by now.
Yes, sir, it is. Oh, sir, this is really my last question. When we were doing, like we did, like 8 BI, and then at the end of, after doing BI, you said therefore F plus G is a linear transformation.
Yes. Yes.
But how did we prove that it's a linear transformation before we proved that V and W are vector spaces?
Well, I started off with the V and W being vector spaces.
Oh, okay. I'm sorry. I just figured it out.
Okay?
Yes, sir.
All right. Next
Thank
question.
you.
Thank you. Next question. Anyone from the remote sectors? Any other questions?
On the, sir?
Yes, please.
On the same number G, that's on the 8 on number G. You said as home V and W, I believe that's a set. It's a set of those vector spaces multiplied by the vector space V. And then you made, say the evaluation W is not linear. Can you please go through again that number G? Something's not adding up for me. Because you've got a set of vector spaces multiplied by the vector space. Can you go through that?
Yes. Sure. Okay. So we saw in C that if you fix an A, this was a linear map, right? The evaluation at A turned out to be a linear map. Now, this one, since we have already shown home VW is a vector space, so home VW cross V by one of our previous results is also a vector space, and we tried to extend that evaluation now. So it is just, I'm making this definition. So I take a pair, I take a linear transformation from V to W, and I take an element A from V. And what is my function doing? It is just evaluating F at A. So that's why I took this function and gave it the name evaluation. But I left it to you to show that it is not linear. It is not a linear map. Remember, what is the linear operation on this? If you have two such, this means this is F plus G as we defined, and A plus B as the defined in V, okay? And lambda times so what I'm trying to say is that it will not be true. So evaluation on this pair is this. This will not be true. Or as well. But this will always be. You see, lambda times FA is also not always true. The lambda times F evaluated as lambda A. Okay? So this is not going to be a linear map. Okay? But we have shown that if we fix an A, this map is linear. This was our evaluation at A. On the other hand, if we fix F, this is also linear. Okay? But, so if I fix one side, then it is linear. So it is linear. Can we say it in this way? It is linear in each variable. But not in both variables. So linearity in both variables would actually mean equations in this and this. Okay? So that's the linearity in both the variables. It is not linear in both the variables, but it is linear in each variable. Remember, if you have gone through a course in multivariable calculus, you also had such problems. It is integrable with respect to x, it is integrable with respect to y, but not with both the variables x and y. Okay? So it is something like this that is happening. Such maps are often called bilinear maps.
Bilinear maps.
We will come to encounter these bilinear maps in a much more crucial way near the end of our course.
Yes, sir. Yes, sir. It's clear. Yeah. It's clear. Thanks.
Any further questions? Okay? If not, then we can disperse. I think it's also time. Yes, it's just the time. We can disperse. And I have given the schedule for March, so you know when and where do we meet. Okay, thank you.
Thank you, sir.